Hey everyone, and thanks for dialing in into this session on F110 autonomous racing. My name is Madhur Bahel. I'm really excited to be here today and to be able to participate. Thanks for the organizers for inviting me to share some of our work in this very, very interesting area. This talk is going to be of a different flavor than probably what you've been hearing throughout the day, because we will take data science and AI and machine learning and bring it to the physical world, to robotics as well. Just a quick means of introducing myself. I'm a professor in computer science and systems engineering at the University of Virginia, and I'm the founder of F110 Autonomous Racing, which is what I'm going to explain mostly and talk about that today. I'm also the director of Cavalier Autonomous Racing. We are an autonomous racing team at the University of Virginia, and now we are moving to race full-scale 200 miles per hour autonomous race cars, and it uses a lot of AI and data science underneath the hood. So let's jump into it, and let me give you a quick overview of what even is F110. And I'd like to begin with sharing this hypothesis, which I believe is going to become true, very, very soon, that really everything that moves today will eventually become autonomous. We are already seeing this happen in many, many different modes of transportation, whether it's vehicles or large-scale hauling trucks or last-mile delivery vehicles for food delivery or drones. And it doesn't matter, what kind of autonomous vehicle we are talking about. All these vehicles have to do the same thing, which is common across all of robotics, right? They have to figure out where they are, what the world around them looks like. And these are what we typically call perception, planning, and control in autonomous vehicles or autonomous systems. And the trend of this sort of field in the last decade or so has been gravitating towards more increased use of deep learning and AI methods to address many of these challenges. And so therefore it becomes very important, as students, as researchers, as academics, we want to be able to test new ideas or figure out if these vehicles are safe. And so we need a good way to try these ideas beyond just simulation or just pure data sets. And it is because of this reason that about 5 years ago, I developed what is called the F110 Autonomous Racing Platform. And really what this is a 1/10 scale prototype of a fully autonomous race car, right? So it's a RC car which can drive itself autonomously up to 20 miles per hour indoors. It's impossible to run behind it and keep up with it. And it's a platform for advancing research in robotics, in AI, in machine learning. It's an excellent tool for education and for outreach as well, and to get students thinking about perception, planning, and control, which is the common DNA for all of robotics. And so what really F110 is it's an ecosystem. It's an ecosystem which has many, many different aspects to it, going from chassis design. How do you build and assemble this car? What kind of sensors do we use? What data we get from the sensors? How do we bring it together in some software which runs on board the vehicle? And then, a lot of different exciting research around autonomy and around robotics and AI is enabled using this platform. And I'm going to share some of that in whatever limited time I have with you today. And so the good thing about this platform is it's completely open source. So anyone can build this, anyone can contribute to the platform itself. We also collaborate very closely with other major open source communities, including Open Robotics, AutoWare Foundation, and OpenCV. And this has grown at scale. I'm very pleased to share that more than 60 universities across the world are using this platform for education, for outreach, and for research, and very high impact research. So these are some of our partners in the US and North America, and we have partners from all over the world who have built these cars, and they come and compete also in international competitions. But more importantly, the reason I like to do F110 is all of those above things, but it's a lot of fun building these cars and getting them to race against each other. So here's a snapshot from my lab at UVA. And I have like more than 20 of these cars that we have built. And so we can do very interesting demos with multi-agent racing and address some very challenging research problems as well. So let's get into what F110 is, how does it work, how you can get involved, and how this can benefit you and your curriculum or your institution, or if you're just a hobbyist looking to enter the autonomous vehicle space, then where to start. So because everything is completely open source, we have organized F110 into these three sort of categories on how to build the car, how to drive the car, and how do you race the car. So starting with the build, we have a detailed instruction set, almost like IKEA-style instructions of how to put this car together in a matter of hours when you have all the parts sourced together. And there's a detailed bill of material on our webpage that I will show you in just a second. But let me show you a quick video on how this car is assembled. Yeah, so about an hour's worth of assembly has gone into those 20 seconds. So like I said, there's a detailed bill of material that you can order, and we have provided links from where to order as well to assemble this car. And what that really involves is you have this underlying base, which is a remote control RC vehicle, and then we add a lot of different sensors on board. We add a powerful GPU NVIDIA computer and some motor controllers, and then we can program the car to become autonomous. And this is very similar to electric vehicle drivetrain that you would see on a road car, but obviously it has different parameters, although it's shares very similar dynamics. Also, it has very similar set of sensors that you would find on full-scale AV prototypes, but at a different scale, because we only operate like a 2D LiDAR or a smaller camera compared to these big power-hungry systems on the full-scale vehicle. And then finally, once you have the car built, you learn how to code the car itself. And so here, this is the opportunity to learn what is called ROS, or Robot Operating System. So this is where all the programming on this car happens. And in light of education around the F110 platform, that is something that is personally a very critical mission of mine. So I have invested a lot in even teaching how to code this car once you have it built. And so I teach a course open source. Sorry, it's completely free and open source. Anyone can go to YouTube and search for F110 lectures, and you'll see a complete playlist of how to begin with ROS. Only background you require is Python. So let me play another quick video of highlights from one of the courses that I taught at UVA. And what you see here is students are learning ROS. So this is what Robot Operating System is. They are learning how to control this virtual turtle inside the ROS, and then we give them the cars. They have some crazy fun in figuring out maneuvers with these cars. Then they assemble the cars together during the course of a semester, and then they go through the paces of making the car autonomous, right? So my course does not have an exam; it has a final autonomous race. So it's very easy to grade based on who finishes when. No, I'm kidding. That's not how I grade. But it's a very exciting course, very popular, and it's completely free and online, available for anyone. And so finally, I've also been organizing international autonomous racing competitions for the past 5 years at prominent robotics, cyber-physical systems, machine learning venues. And so far, we've organized more than 8 competitions, including a virtual race in 2020 because of COVID. So we switched to an online simulator. And the idea of all these races is that people use our open source materials to build and assemble the car. And so all cars have the same sensors. They have similar spec. And the only part of the competition that you can have an advantage is it's a battle of algorithms. So that's the only way to outsmart other teams. So here's a short video of highlights from one of our competitions, which was held a couple of years ago in Italy. We were literally racing smaller cars in the backyard of where Ferrari's factory is in Modena in Italy. So let's look at this quick highlight of that competition. So you can see some teams are building, sophisticated maps of the track. Others are probably doing something a little bit more simpler, figuring out where the space is to drive. And like I said, we have teams from all over the world who come and race. Yeah, so this is just a quick highlight video to give you a better sense of this competition. Here's a video from a race that we held in Montreal in 2019. And I think this gives a very good sort of perspective on how fast these cars are. So you can see this is not like a slow robotics demo in some control lab. These cars are racing each other, right? This car is actually trying to overtake the other F110 car. It's trying to figure out, they almost collide over here, but you will see on the next lap, the car actually manages to overtake on the inside. And that's what it's all about, right? So this is the sort of cutting edge research that we want to do with this vehicle. So speaking of which, the vehicle has a very realistic software pipeline, which addresses all three aspects of autonomy, from perception to planning to control. Talking about perception, we have a lidar on board the car, which can sense the hallway or the surroundings and give you like a scan of what the world looks like, as is shown here. And then we go deeper, and where we look at rigid body transformations on the vehicle, and we can teach you about what are these different transform frames, and how do you take data from one sensor frame and use it to figure out where the car is in the world itself. Which brings us to some planning and localization algorithms. So here you will see this vehicle is being driven in a hallway using just a remote control, so it's not autonomous yet. But on the right-hand side, you can see as the vehicle is being driven, we are generating a live map or a scan of this hallway, right? As it discovers these unexplored areas of the hallway using this LiDAR that it has on board, it can build this map in real time and keep track of how it was driven in the world itself. And so this is very useful because once you have this map, you can learn how to control the vehicle using PID or even advanced control. So here's a quick video of a controller which is trying to keep the car true on the center of this corridor, as close as possible to this virtual red line, which is the center of this corridor. So when your controller is good, you do a good job of following the line. But if your controller is not tuned, you will veer away, and then you will oscillate around the line. So you can teach the principles of control using this platform as well. And when we bring this all together, now what you are seeing in this demo is you have a car which already has the map, but now it's running autonomously, right? So it's taking the map, it's taking the control algorithm, and what you see is the blue is where the car thinks it is in the world. And so it's able to localize itself using what we call a GPU particle filter, which uses something called scan matching. And again, these are all things which I teach in the course online, and anybody can pick this up. All right, so finally, let me talk a little bit about the kind of research that this platform enables before concluding this presentation. And as you can see, we have gone incrementally from building the car to learning about perception, planning, control, but we don't stop there. We want to push the limits of what is possible with autonomy, with high-speed racing. In fact, I would say in motorsport racing, there is a saying that if everything seems under control, then you are not going fast enough, right? This is how racing drivers think when they race. And in a nutshell, this is a data science conference. You can think of the research that my group does as we are trying to train an AI with this statement as the objective function. That's our goal. That's the goal of the algorithm. Can you drive at the limits of control of what is possible? So again, we start with very basic algorithms, right? So just doing wall following. Can you look at where the track is on the left and the right side? You can see the track is elevated, so the LiDAR can get clean scans of like this hallway or this track. And you just try to find your optimal trajectory on racing in this track in the absence of any other cars. But you can do something even more complex, right? So you can do collision avoidance. So now the car is not only trying to just keep itself aligned in the center, it's actively avoiding collisions based on the data it is receiving from the sensor. So a lot of clever algorithms like follow the gap are being used here. You can see there's barely any space for the car, but it does such a nice job of going cleanly through this small little gap. And so in our competitions, teams come, and then we have what is called time trial. So you have to put in a number of laps. We look at your average lap time. We look at your fastest lap time. There are penalties for causing a collision or colliding with the track itself. And so this is you can see how when you're going around the 60 feet of track in less than 9 seconds. So it gives you another idea of how fast this car is. And we, again, can make it more complex. Another area of research is in motion planning. So here we are planning or coming up with algorithms that are figuring out how to navigate in a cluttered environment without knowing that where these cubes are previously, right? So that we can move these cubes around and the car will still be able to plan its way around these obstacles. Speaking of deep learning and AI, we have built YOLO-like detectors. So we use deep learning and artificial neural networks and OpenCV to build detectors that can detect other cars, because we want to graduate from single vehicle to multiple vehicles on the track. And this is a demo of how well that works. You can see it's able to figure out where the car is, and we're also able to figure out the pose of the car, so what direction the car is and how fast it is moving. And finally, we cannot have a talk in a data science conference without talking about end-to-end learning. So we are able to run a neural network on this car, which can autonomously navigate or steer the car. So here you can see the alignment between the prediction of the algorithm and the ground truth of the steering of the vehicle. And so just to give you a little bit of context, here's my student. He's driving this car in my lab, and he's wearing a first-person view headset while he's driving. So it's almost like he's playing a video game, but with the real vehicle. So he's steering, and he has the throttle and brake control as well. And as he is driving, we get a lot of data. So you see the LiDAR scans, the camera image, the IMU or accelerometer data. And so we have all this data that we can feed into our deep learning algorithms, right? So here is a special scenario where he's driving one car and the other car is just doing wall following. And he's trying to create situations of overtaking this other vehicle. So he's manually overtaking, and this is what that looks like from his perspective. But we are logging all this data and training our deep neural networks to then learn how to autonomously overtake. And so when you put this together, here's a vehicle which has learned how to autonomously overtake in that same track, right? So you can see the vehicle is kind of overtaking from the inside, kind of like racing drivers do. And it can also overtake on the straight, just like it was shown in the human demonstration. So it's a pretty impressive stuff that you can do with deep learning on this vehicle. So in a nutshell, there's a lot of scope for interesting research. I hope this is just a tip of the iceberg as far as an introduction on what is possible. And we are looking forward to what more the community has to offer, making it even more accessible to high school students or to freshmen and undergraduates and so on and so forth, or even non-engineering majors. In line of research, I've also developed what I call the simulator platform. So this car, although it's very useful, it's not it's reasonably priced, but the car sometimes you cannot access it, or some parts are out of stock. So that shouldn't stop you from learning, and therefore we've developed a simulator which can do all of what I just showed you, right? So we can build the map, we can localize ourselves within the map, similar to what I showed you. And then we can do motion planning, like what I showed you in the real car as well. So everything you can do in the simulator, and then you can translate that to the real world, right? So you can do this advanced kind of planning. So here's another cool video of driving at the limits of control. So you will see this car as it comes around the corner, it's so fast that the wheel will lift off the ground. So you can see the wheel actually comes from the ground. It lifts off. And that's how we are pushing these algorithms of the AI and the self-driving stack to the limits of what is possible. The car is almost tipping, but the controller then brings it back forward. So I only have a few minutes left. I want to get to some other interesting stuff soon. So let me skip this forward. One of the things I've also done in my lab is use simulation and game to advance autonomous research. So here you will see on the left-hand side is a video game of racing used by real racing drivers, and on the right-hand side is real footage. So you can barely tell them apart. And what my group is the first in the world to design an AI algorithm that can drive autonomously in this photorealistic environment. So we can race autonomously in this game at very high speeds with a clean lap, and we have even beaten some human lap times with our AI algorithm. So this work is called Deep Racing AI. I encourage you to look it up and check it out. And enough said about the 1/10 world. To conclude this talk, I will show you just one last piece where I also lead this Cavalier Autonomous Racing Club at my university. And what we are doing is we are scaling this up to the full-scale race car, right? So in October of this year, our university will be one of very few to compete in a $1 million competition where we will race full-scale 200-mile-per-hour autonomous race car. And if you don't believe me, and this is a computer-generated image, then this is the real deal, right? So just last week, we were in Indianapolis working on this full-scale race car, which is basically now 10x this 1/10 for. So everything we have learned on the 1/10 scale can be now translated to this full-scale vehicle, which has the same perception, planning, control problems. So we debug the car inside this workshop, we take it to track, gather all the data, and so on and so forth. So to conclude this talk, I'm going to stop here because I'm almost out of time. This was a very fast pace. If it's racing, it has to be fast paced, but it's a very fast paced introduction to F110 autonomous racing. And I challenge you all who are listening to this talk to check us out and see if you have what it takes to be the best autonomous driver. So that's my time. My email ID is at the bottom of this slide. And your single resource, or if there was one thing you take away from this entire talk, is to visit this webpage called f110.org. And it will have all the resources and materials that I shared today for you to get started. If you want to know more or need some help in your institution to get involved in this program, please feel free to email me at this address, and I'll do my best to get in touch with you. So thanks again for dialing in, and that's my time.